Hello, this is Dr. Pablo Rivas, and I'm talking today about our paper, Quantum Geometry Alone Does Not Predict Kernel Utility. Thank you for joining. This talk asks a narrow but important question. When quantum kernel looks geometrically different from a strong classical kernel, does that difference actually predict downstream utility? In the completed evidence set, the answer is no. Geometry alone was not enough. Quantum kernels often are screened before training with geometry-based cores, and that's useful, but the matrix used for training may be estimated with finite shots exposed to noise, prepared to recover positive semi-definites or poorly conditioned. Those details matter because SVM does not train on an abstract ideal object. It trains on the matrix we actually compute. I will show 4 results today. Strong classical baselines remained it hard to beat. Large geometric difference did not predict balanced accuracy. Kernel-target alignment was more informative in this evidence set. And shot and noise settings changed matrix validity. I will close with a 4-part screening workflow that combines geometry, label alignment, matrix quality, and classical utility. This screening problem has 2 parts. The first question is geometric. Does the quantum kernel define a representation that differs from a strong classical reference? And the second question is more operational. If we train an SVM with that kernel, does prediction improve? A large geometry score addresses only the first question. Our evidence contains 271 quantum kernel SVM evaluations and 780 tuned classical SVM evaluations. We define a quantum kernel as useful only when it exceeds the best classical baseline by a balanced accuracy margin of 0.01. Under that rule, none of the 271 quantum rows were useful. That result does not mean the experiment failed, it just reveals the screening gap. A kernel can look different and still not help. The purpose of screening is therefore not to celebrate difference. It is to identify candidates that are different in a task-relevant, numerically valid, and practically useful way. The rest of the talk asks which signals help us make that decision before larger computations. Here's the mechanism. A classical input X is passed through a quantum feature map circuit. The circuit prepares a state, which we write as C of X. For 2 inputs, the kernel value is the squared overlap of their assets. Repeating this process for all train and test train pairs creates a gram matrices used by a standard support vector machine. The learning algorithm is classical. The quantum cost is matrix construction. The distinction matters because the SVM step is fast once the matrix exists, while kernel estimation can require tens of thousands of circuit evaluations for one experimental row. The study asks whether scores computed from ideal metrics remained informative when the matrix is estimated with finite shots or simple noise models. If the measured matrix loses positive semi-definiteness, becomes poorly conditioned, or aligns weakly with the labels, then a promising ideal geometry score may not describe the object that the classifier usually uses, or actually uses. That is why we evaluate both screening metrics and downstream SVM performance under match conditions. The design is deliberately conservative. We do not compare quantum kernels with weak or unwanted baselines. For each data split, we tune linear, RBF, polynomial, Laplacian, and random feature SVMs. Then we use the strongest classical result as reference. The quantum side uses 3 4-qubit feature maps across synthetic and real datasets. The completed evidence set includes exact kernels, finite shot estimates, clean simulation, and simple nose channels. For each quantum row, we recorded geometric difference, kernel-target alignment, condition number, eigenvalue diagnostics, and downstream accuracy. The utility rule is strict but easy to interpret. A quantum kernel is useful only if it beats the strongest tuned classical baseline by at least 0.01 in balanced accuracy. This prevents small numerical fluctuations from being labeled as practical gains. It also separates the question of representational novelty from the question that matters to a user. Does the model improve prediction enough to justify the extra kernel computation costs? Well, this is the central performance results. The vertical axis shows the balanced accuracy gap between each quantum kernel SVM and the strongest tuned classical SVM. 0 means a tie. Positive values would indicate a quantum improvement. Across all 271 completed quantum rows, no row exceeded the classical baseline by a positive margin of 0.01. Only 4 rows were non-negative, when the margin was reduced to 0. The strongest classical models were especially difficult to beat on the real datasets, where linear or RBF kernels often reach very high accuracy, as it's normal. The correct interpretation is not that useful quantum kernels cannot exist. The evidence set is limited to the test datasets, 4-qubit maps, and simulation conditions. And of course, this could escalate depending on the hardware noise and how that evolves over time. The result we present here is narrower and more practical. In these experiments, representational difference did not produce a predictive gain. That makes the study a screening paper, not an advantage paper. It asks how to reject false positive promise before committing to larger matrices, more seeds, more qubits, or hardware execution. Geometric difference is intended to identify when a quantum kernel defines a geometry that differs from a classical reference. In our findings, this score was often extremely large. The mean geometric difference against the strongest classical reference was about 6,680. But the practical question is whether a larger score predicts a better classifier. The global same condition Spearman correlation between geometric difference and quantum SVM balanced accuracy was 0.007. In other words, there was essentially no useful monotonic relationship. The scatter plot shows why. Large geometry scores occur at low, medium, and high accuracy values. Geometric difference tells us that two kernels are not equivalent, but it does not tell us whether the quantum geometry is aligned with the classification task. This distinction is the paper's main warning. Geometry remains valuable as an initial diagnostic, especially for ruling out near equivalent kernels. But it should not be treated as a standalone training decision or as a proxy for downstream utility. For that, we need more and different experiments. Kernel-target alignment, or KTA, as we will refer to it moving forward, was the strongest screening signal in the completed evidence set. Unlike geometric difference, KTA is label aware. It asks whether the structure of the kernel matrix is consistent with the target labels. Same label points should be similar, while different label points should be separated. The global same condition Spearman correlation between KTA and balanced accuracy was approximately 0.526. That's not perfect and is not a universal theorem. It is an empirical result of this study, but it's clearly stronger than the near zero association for a geometric difference. The two panels make the contrast visible. On the left, KTA leads the metric ranking. On the right, higher KTA generally accompanies higher downstream accuracy. This supports a multi-metric view. Geometry can show that a representation changed, while KTA helps determine whether the change is relevant to a task. KTA should be still combined with matrix quality checks and classical baseline comparisons rather than used as a single replacement score. The next result concerns numerical validity. A kernel used by an SVM should be positive semi-definite. Finite shot estimation and noisy simulation can violate that property because every matrix entry is estimated separately and sampling errors do not automatically preserve the global PSD constraint. In the completed evidence set that we presented in the paper, 67.3% of raw kernel matrices had at least one negative eigenvalue. The distribution varies across shot and noise conditions, which means the numerical quality of the measured metrics depends on how the kernel is estimated. Positive semi-definite grouping removes negative eigenvalues, but that repair can change the matrix. It's therefore a useful diagnostic event rather than a free pass. If substantial repair is needed, the trained classifier is no longer using the raw measure kernel. This matters for pre-screening because an ideal geometry score may describe a different matrix from the one ultimately passed to the SVM. Matrix validity, conditioning, and repair magnitude should be checked before interpreting predictive results. The practical output is a four-part screening workflow. First, we ask whether the quantum geometry differs from a strong classical reference. Second, ask whether the kernel aligns with the labels. Third, inspect the matrix. Is it positive semi-definite, stable, reasonably conditioned under the actual shot and noise setting. Fourth, train the downstream model and compare it with the strongest tuned classical baseline. This workflow does not discard geometry difference. It just assigns the metric a specific role. Geometry is one signal, not the final decision, and label alignment adds task information. Matrix diagnostics reveal whether the estimated kernel is safe to use. Classical comparisons established whether the extra quantum computation produced practical value. The main idea is just risk control. Quantum kernel matrices are expensive, and the cost grows quickly with sample size. This is a known fact. A candidate should survive all four questions before we commit to larger matrices, additional seats, higher shot counts, more qubits, or hardware runs. That is the meaning of shot and noise aware screening in this paper. In this slide, we define the boundary of the paper. We do not claim that we have quantum advantage. We do not introduce a new metric. We do not prove that geometric difference is wrong, and we do not report hardware evidence. The claims are narrower and supported by the data. First, geometry alone can overstate practical promise. Second, KTA was more associated with downstream accuracy in this particular evidence set that we present. Third, finite shot and noise estimates created matrix quality problems. Fourth, strong classical baselines are required before making any claim about quantum utility. That bounded framing is a strength. It keeps our paper focused on operational questions that we researchers face now, which is what candidate kernels deserve more computation? The answer is not to stop using geometric difference. The answer is to use it as part of a broader decision process. A trustworthy screening conclusion should survive label-aware metrics, matrix diagnostics in a direct comparison with tuned classical models. Kernel computation becomes expensive quickly because kernel methods require pairwise train, and test train similarities. As sample size grows, the number of circuit evaluation grows roughly quadratically. The runtime plot shows the large increase between the 100 sample and the 250 sample setting. The paper reports all the evidence that is finished cleanly. The broader research program adds more seeds, larger samples, higher shot reference, and 8-qubit checks. Those runs are computationally substantial, especially under noisy mixed state simulation. This cost is not just an engineering detail, it just motivates pre-screening. Once a matrix exists, the SVM trains in seconds. The expensive step is quantum matrix construction. A screening workflow that rejects weak candidates early can save days or weeks of simulation and eventually valuable hardware time. The goal is therefore not only better interpretation, but it's a better allocation of quantum computing effort towards kernels that have evidence of task alignment and numerical validity and practical utility. I'll close with the simplest statement of the result. If a quantum kernel only looks different, that's not enough. A candidate should be screened in 4 dimensions: geometry, label alignment, matrix quality, and downstream utility against strong classical baselines. In the results presented in the paper, geometric difference was large but essentially uncorrelated with balanced accuracy. KTA was more informative, and finite shot or noisy estimates often produce PSD problems. The contribution is therefore a safer decision process for quantum kernel research. It does not end the search for useful quantum kernels, but it helps us spend compute where the evidence is strongest and avoid treating geometric novelty as predictive value. Thank you for your attention, and I welcome questions about the screening metrics, experimental design, or anything you have. Contact me by email, and we'll look forward to hearing from you.